Module 3, Section 2.6, Logarithmic Functions. Objectives. Objective 1. Understand logarithmic functions, its graph and its properties. Objective 2. Evaluate logarithms. Objective 3. Solve applications involving logarithms. Objective 1. Logarithmic functions. There is a close connection between a logarithmic function and an exponential function. The logarithmic function and exponential functions are inverse functions. A function f is said to be 1 to 1 if each range value corresponds to exactly one domain value. Here is an example of the graph of a 1 to 1 function. If x is equal to 0, then y value is 1, and if x is equal to 1, then y is about 2.8. Now if we choose any pair of x values, we see that the corresponding y values will always be different. Definition of inverse function. If f is a 1-to-1 function, then the inverse of f is the function formed by interchanging the independent and dependent variable for f. Thus, if a comma b is a point on the graph of f, then b comma a is a point on the graph of the inverse of f. Also notice that if a function is not 1 to 1, then f does not have an inverse. Let's look at the inverse of the exponential function. If we start out with y equal to 2 power x, and if we interchange x and y, then we will get x equal to 2 power y. There are no algebraic techniques that can be used to solve for y, so we simply call this function y the logarithmic function with base 2. The definition of this new function is log to the base 2 of x equal to y if and only if x equal to 2 power y. This shows the graph of y equal to 2 power x and the function y equal to log to the base 2 of x, which is the inverse of y equal to 2 power x. Notice that these two graphs are symmetric with respect to the line y equal to x. This table displays how the points are correspondingly related on the graph. In general, the inverse of an exponential function is called a logarithmic function. For b greater than 0 and b not equal to 1, we can say that y is log to the base b of x if x is equal to b power y. The log to the base b of x is the exponent to which b must be raised to obtain x. The domain of the logarithmic function is a set of all positive real numbers, and the range of the logarithmic function is a set of all real numbers. Here we are going to graph log of x plus 3. Select a window, negative 10 to 10 for x and negative 5 to 5 for y. If we press graph, we will get the graph of y equal to log of x plus 3. To graph the second function, we need to type in 3 times. So notice that this will be ln, so we need to use this key up here. The graph will look like this. In this example, we are graphing y equal to 4 times log of x minus 2. We type in the formula, and if you select an appropriate window and press graph, we will get the graph like this. So notice that this graph is increasing, and we need to find the increasing and decreasing intervals. So this graph is consistently increasing for x greater than 0. So the answer to the first question will be increasing in the interval 0 to infinity. The answer to the second part of the question, find the decreasing interval. So this function is not at all decreasing, so we can answer this as never decreasing. Logarithmic exponential conversions. Let's study the examples below. we should be able to convert a logarithmic expression into an exponential expression and vice versa. Log to the base 4 of 16 equal to x can be written as 4 to the power x equal to 16. So that means x has to be 2. Log to the base 3 of 1 by 27 will be written as log to the base 3 of 1 by 3 to the power 3, and 1 over 3 to the power 3 is 3 to the power negative 3. So we will get log to the base 3 of 3 to the power negative 3 equal to negative 3. So this is another equation which is written in the exponential form. We can now write this in the logarithmic form like this. Log to the base 5 of 125 equal to 3. If square root of 81 equal to 9, we can write it as 81 to the power 1 half equal to 9. That means the square root is power 1 half. And then when we convert to the logarithmic form, log to the base 81 of 9 will be equal to 1 half, which is the exponent up here. Let's do a few examples. Rewrite the expression log to the base 2 of 32 equal to 5 in an equivalent exponential form. So this will be answered as 32 is base is 2, so 2 to the power 5. So these two are equivalent. Write the equation in equivalent logarithmic form. 27 equal to 9 to the power 3 by 2. So if we calculate logarithm of 27 to the base 9, written like this. So log to the base 9 of 27 will be this exponent here, which is 3 by 2. So that will be the answer for this question. Solving equations. Using the definition of a logarithm, we can solve equations involving logarithms. Here are some examples. Log to the base b of 1000 equal to 3 means that b to the power 3 equal to 1000. But 1000 is 10 to the power 3. So we can write b to the power 3 equal to 10 power 3, which implies that b is equal to 10. In the second example, we are getting log to the base 6 of x equal to 5 converted to the exponential form. 6 to the power 5 will be x. So the x value will be 6 to the power 5, which comes out to be 7776. In each of the above, we converted from log form to exponential form and solve the resulting equation. Evaluate log to the base 51 of 1 without using a calculator. We know that 1 can be written as 51 to the power 0. So therefore, log to the base 51 of 1 will be equal to 0. Calculate log to the base 10 of 1 million without using a calculator. So 1 million is 10 to the power 6. So that means that log to the base 10 of 1 million equal to 6. If log to the base 121 of x equal to 1 half, find x without using a calculator. So we need to write this in the exponential form. So the number x will be equal to base 121 to the power 1 half. So which is also the same as square root of 121. When we calculate square root of 121, we are going to get 11. Find y from the equation log to the base 2 of 8 equal to y. So here we can write 8 equals 2 to the power 3. So therefore if you rewrite this as log to the base 2 of 8, we are going to get 3. So the value of y is 3. Here are some important properties of logarithms. Log to the base b of 1 is always 0. Log to the base b of b is 1. Log to the base b of b power x is x, and so on. This property says how to calculate logarithm of a product. So log to the base b of m times n will be equal to log to the base b of the first factor m plus log to the base b of the second factor n. Here we are calculating logarithm of a quotient. Log to the base b of m over n equal to log to the base b of the numerator minus log to the base b of the denominator n. So here it is the logarithm of a power. Log to the base b of m power p equal to p multiplied with log to the base b of m. Log to the base 10 of x is called the common logarithm, and we will write it as log x without the base indicated there. And log to the base e of x, where e is the natural base, it is called the natural logarithm, and the notation for that will be ln of x. If no base is indicated, the logarithm is assumed to be base 10. Example: evaluate the following using a calculator. The first one is a common logarithm, so we need to use the log key here. Log of 4305.3. That answer will be 3.634 corrected to 4 decimals. In the second case, we are getting a natural logarithm, so we need to use the natural log key. So that comes out to be negative 2.6908. Expand the expression using properties of logarithms, and if possible write the answer without exponents. So this will be common logarithm of x to the power 6 over 11. So if we use the quotient rule, we can write it as logarithm of the numerator minus the logarithm of the denominator, and now we can use the power rule. So this will be like 6 log x minus log of 11. So that is the answer. In the next example, again use the properties of logarithms to write the expression in terms of logarithms of x, y, and z. So notice that this is the natural log notation. So I can write this again as natural log of, this is a fraction, so we need to write the numerator x y to the power 5 minus natural log of the denominator c to the power 4. Now in the first logarithm, it is a product, so I can write natural log of the first factor x plus natural log of the second factor y power 5 minus natural log of c to the power 4. Now we can simplify this one more step. Y to the power 5 and c to the power 4, these are powers, so I can use the power rule. So my final answer will be natural log of x log y to the power 5 will be written as 5 multiplied with natural log of y. So plus 5 times natural log of y, then minus 4 times natural log of c. Solve symbolically and support your answer graphically. So I'm going to write this as log of x multiplied with x plus 21 equal to 2. That is using the product rule. Logarithm of a product is sum of the logarithms. Now again I can write this as x multiplied with x plus 21. Here the base is 10, so I can write the power notation 10 to the power 2. That will be equal to 100. So this is converting the logarithmic equation into an exponential equation. When I multiply this, I will get x squared plus 21x, and if I move the 100 over here, that will be minus 100 equal to 0. So I need to solve this equation. Factoring can be used. X plus 25 multiplied with x minus 4 equal to 0. So that gives 2x values, x equal to negative 25 from the first factor and x equal to positive 4 from the second factor. But notice that log of x is defined only for positive real numbers. So therefore I cannot take this negative value. So this is ruled out. So the only value that comes as the solution to the equation will be x equal to 4. So this is the only value. So this is going to be the answer. To solve this graphically, I take y1 and y2 as the left hand side and the right hand side functions. Now if I select a window from negative 10 to 20 for x and negative 5 to 8 for y, I will get the graph like this, and I can calculate the intersection point, and the intersection point is 4, 2. So the x value of the intersection is the solution, and we get again x equal to 4. Few more examples. Solve 3.127 to the power 13x equal to 5. This is an exponential form, and we are going to write the logarithmic form of that. So natural log of 3.127 to the power 13x will be equal to natural log of 5. So which is simplified as 13 times x natural log of 3.127 equal to natural log of 5. When we solve for x, we will get x equals natural log of 5 divided with 13 times natural log of 3.127, which will come out to be 0.1086. Here we are getting an exponential equation, so we need to convert to the logarithmic form. Notice that the base is e. So if I take the natural log on both sides, the left side we will get x, on the right side I will get natural log of 5.386. So natural log of 5.386 is 1.6838. Solve the equation natural log of x equal to 3.1416. So this time we need to convert to the exponential form. The base is e here. So x will be written as e to the power 3.1416. And when we compute this, we will get 23.1409. And these are the calculator entries. Application. How long will it take money to double if compounded monthly at 4% interest? So here we have the compound interest formula, a equal to p multiplied with 1 plus r over m to the power mt. Replace a by 2p, which is doubling the amount. We will get this equation, and if we cancel out the p, we will get another equation, 2 equal to 1 plus 0.04 by 12 to the power 12t, which is simplified as this. And this is an exponential equation. Variable is in the exponent. We convert to the logarithmic form, and then we can get a linear equation in t, and dividing with the coefficient we will get t as 17.36. And here is our last example. How many years will it take 1,000 to grow to 10,000 if it is invested at 5.25% compounded continuously? If the interest is compounded continuously, we need to use this formula, a equal to p multiplied with e to the power rt, where a is the future value, p is the principal or the deposit amount, r is the annual rate in decimals, and t is the number of years. So when we put the numbers, we will get 10,000 equal to 1,000 multiplied with exponential. Rate is 5.25%, which will be 0.0525 as a decimal, then times the number of years is t. So if you divide both sides by 1,000, I will get 10 equals exponential 0.0525 multiplied with the t. This equation is what I need to use to solve for t. So if I take the natural log, I will get natural log of 10 equal to 0.0525 times t. So that gives the t value as natural log of 10 divided with 0.0525, computed as 43.86 years.